Hello, everybody. Welcome to an exciting and interesting, unique episode of this show. I'm not telling you the name because this is actually two shows. We are joined in the studio today with the hosts from the Adventures in Machine Learning podcast, Michael and Ben. And then from Adventures in DevOps today is me, Jonathan, and Jillian. So we're going to do a crossover episode and talk about DevOps and ML and whatever else happens to come to mind today. Before we dive into that conversation, why don't we do a brief around the room and introduce ourselves? Michael, do you want to start?
Sure, I would love to. Thank you for the intro. My name is Michael Burke. I'm a resident solutions architect at Databricks, so that means I just do a bunch of random crap. Sometimes it's building machine learning models, sometimes it's implementing data infrastructure or data architecture. And then my background is in sort of A/B testing and machine learning as well. So I'll kick it over to my co-host, Ben.
Hey everybody, I'm Ben. As Michael said, co-host of Adventures in Machine Learning podcast. By education and early work, I was a nuclear engineer. Didn't enjoy that. Got out of that and the Navy and worked in process engineering at a bunch of factories, which led me into data science, which led me into wanting to write better code, which becoming a machine learning engineer. And then got hired by Databricks, worked in the field for a while. Now I work on building ML ops tooling, such as ML Flow within engineering at Databricks. Also the author of Machine Learning Engineering in Action by Manning.
Very cool. Jillian.
Yeah, that is very cool. I'm going to have to ask you about ML Flow. So I'm Jillian. I used to work as a bioinformatician and then kind of slowly but surely moved more onto the kind of computational side of things, was an HPC sysadmin for a while, and then moved more into this, kind of field that we call DevOps, where mostly I work with, as an independent consultant, I work with biotech companies, and I help the data scientists get their pipelines and their code into production, wherever that happens to be. Usually it's on AWS, but it could be on their systems. Sometimes it's sort of your standard statistical pipelines. Sometimes it is more machine learning pipelines, and that's always kind of fun when that happens. And sometimes it's other kind of tools like very high performant data visualization applications where you have data, it appears in a browser, but behind that you have, maybe like terabytes of data hanging out in the back end that all have to be presented for a scientist to be able to view quickly, because people don't want to have to wait for their buttons to spin around and finally show them data.
Very cool. And I'll round out the intros. I'm Jonathan Hall. I kind of do a little bit of everything, back-end dev work, DevOps work. Lately, I'm helping a couple different companies, one with some Go development, and another with some PHP. I'm diving into PHP again. I haven't done that in about 10 years. So, a little bit of everything. So, what are we talking about today?
The intersection of ML and DevOps and what these terms actually mean. With respect to how you would apply DevOps principles and not necessarily technology to ML. Before we started, recording, we were chatting a bit about, what are the fun things that we could all talk about together, and turns out there's a lot.
So let's start, because I think when people hear DevOps and ML, the first thing that's going to pop to everybody's mind is ML ops. Do one of you guys want to tackle that, Michael or Ben? What is ML ops, and is it a useful term in the first place?
Useful. I think it's good to have a label for things.
Mm-hmm.
It's bad when that label is so ambiguous and nebulous that nobody knows what it actually means. And if we were to go back in time 15 years ago, maybe 20 years ago, .com bubble was, growing, getting really big. People were writing a lot of not so great code, just trying to push stuff out there, make some money, get acquired by a big tech company. That's the thing that created San Francisco as it is today, and built Palo Alto. People realized at that time, like, hey, we all need to subscribe to some sort of process around how we build software, how we deploy it safely, how not to get woken up at 3 a.m. on a Saturday because your code blew up in production. And what are all those controls that we need? What are the things, what are the processes that need to be in place? And in any solid engineering practice, you start with those processes of what you need to do, and then you build software to automate that stuff. And I think that's what people associate with DevOps today, who aren't actively involved in traditional software engineering. They're like, oh, it's those tools. It's like it's Terraform. That's DevOps, and our CI/CD platform where we're using GitHub Actions. That's DevOps. It's like, no, it's the process. Doesn't matter what tool you're using. It's that whole concept of we write code, we get it reviewed, we make the changes, we push the changes, we test, and we do this full life cycle of people. Everybody who has distinct roles are interacting with one another in order to get the end goal, which is software running well in production. There's a whole bunch of other theory around that. But if we were to go back 20 years ago and look at what that was, that's where MLOps is now. Mm-hmm. People are like, yeah, we know there's things that need to happen. We don't know what they are yet exactly. We don't know the most optimal way to do it. So people are just kind of lumping a bunch of stuff in. Like, oh, I need explainability. That's really important. So that's part of MLOps. And I need tracking. That's really important. And I need, to be able to do hyperparameter tuning and track all of that. And that's all going to be in MLOps. It's like, kind of, I guess. But it's just an overly loaded term that refers to too many things right now because people haven't all agreed and the tooling hasn't completely been built out that does all of the things that you need to take an idea from its initial concept to something that's shipped to production is running continuously. That's my take on it.
Any disagreement from you, Michael?
Yes, tons of disagreement.
Great.
No, I think that's aligned with my understanding as well. One point I would like to highlight that Ben stated was sort of the MLOps development in a historical sense is pretty nascent and pretty underdeveloped. Mm-hmm. Where software was about 20 years ago, give or take whatever number of years. And so there's a lot of work that needs to be done. And I was wondering if we could kick it over to you guys, because I was wondering this myself. What is the reason that ML is different from software? Like, why is it more quote unquote complex or just different?
I think I'll give my short answer so that I can say something at all, because as soon as I hand it over to Jillian, she knows this stuff better than I do, and she's going to just make anything I say sound like child's play. I think the big difference is that ML is software is mostly building logic. Mostly, it's not entirely building logic. There's also assets. There's sometimes graphical assets or data assets, whatever. But it's mostly building logic. Whereas ML includes logic, but it has a huge component that is data and a model, and those things don't fit well into the brains of software developers all the time. Like, how do we handle these other types of things? I don't know. So I think that's probably the biggest difference. I mean, there certainly is a software component to ML, but there's those data models, and then the data that feeds them or that it acts upon, I think makes it different. So I think that's the biggest difference. But I'm really curious now if Jillian can either correct me or expand on that.
So I agree with you on a lot of points. I wouldn't say software is a solved problem, but I would say it's a lot closer to being solved, and we understand the parameters, right? Like software kind of as its core hasn't changed that much since I took, intro to computer science considerably longer ago than I'm willing to admit, right? The data structures are all very similar. We have lists, we have dictionaries, we have linked lists, we have functions, we have classes, right? These are all kind of fairly standard things that you see sort of across the board within software. We have, my favorite is a for loop all the time, always. So we have all these things, and for the most part, if you can kind of read software from one language, unless it's got like super duper ridiculous layers of abstraction, just across the board, you can kind of look at it and see what it's doing. And I would say that's not true for data. Data is a lot more complicated. That's why, in ways that we don't know what we don't know. So for example, if you look across maybe the last 10 or 15 years, how many different kinds of databases have there been, right? We had relational databases, and then everybody was like, no, that's too structured. Let's have, MongoDB and document databases, and then let's have like Redis key value stores, and maybe we should just stick everything in Elasticsearch because, why not? And we're kind of constantly evolving these ways to have data and to reason about data. And then not only with that, when you have a data set, quite often you have to track the history and what's called like the data lineage of that data. And it happens in multiple places, right? So maybe software, like we could say, it basically happens in my IDE. That's not true of data. So I work with bioinformatics and genomics data. So, let's say that we're collecting, blood samples from a person in a clinical trial. There are so many different places where something could go wrong with that data. There could be, the person drank a bunch of crazy energy drinks before they went in for their diabetes blood draw, or the nurse who was drawing the blood could have mixed up some tubes, or somebody might have been eating lunch in the lab that day when they were running running the blood tests through the sample. The genomic sample could have been kind of wonky. Once you have the raw data, there's like so many different ways that you can process that. So you can just see like all across the line, there are so many different places where something could have happened that affected that data. So I think data is much more of like an open system, whereas software is much more of a closed system. And I don't know that I quite like that terminology, but that's what I'm gonna go with for the moment.
Yeah, I mean, I'd agree with that quite a bit. Even the myth that people have of, let's say we all work at a startup together, and
all right, on three, 1, 2, 3, we all work at a startup. Guys, come on.
So if Jonathan, you're in charge of creating the app, and you've created a front end that users interface with, and that's sending data to Jillian, who's running the entire backend system, who's processing all of that, parsing that JSON, getting into a structured format, which then goes to Michael, who's our data engineer, who's taking that and putting that into a format that can be saved into either a relational table or a data warehouse somehow. And then if I'm working as the data scientist, I might think, hey, we know where the data came from. We know what the structure was. We have strong typing controls on every phase of this process. What happens when we need a new product feature? And Jonathan now adds four features to the data. Jillian now has to update all of that on the back end to process that, and Michael's got to change his data engineering code. Fast forward 4 months, oops, we didn't need those 3 features. In fact, one of them is just wrong. Our logic was bad. So even with those controlled systems that people assume are going to be sacrosanct, they never are over time. Mm-hmm. They are at a particular point in time. We can have our tests, validating that everything works correctly, but over a long duration, things go wrong. And in the data world, I don't know if there's really good tools right now to correct for that. You can detect it, but how do you coerce data? With the
that
genomics
is why
example.
We have clinical trials.
Yeah, exactly.
Right? Yeah, no, I agree with you. There are no really good ways to track that. So you have to have some kind of end test in mind where you say okay, is this working the way that we say that it's working? And you have to have some way to verify it. In genomics, you have to be able to verify things usually in a lab or in a clinical trial.
One of the things we do in DevOps, using the word loosely, is this concept of everything is code. Infrastructure is code, deployments is code, whatever. GitOps is a buzzword these days. And the reason for that is I think it solves the same problem you're talking about, but for a different problem domain. It solves the problem. What was the state of our configuration and our infrastructure on January 3rd when the system crashed? We can figure that out, and we can revert. In theory, at least, we can revert or rewind it back to that last known good state. I think you're just saying basically we need something to solve that problem for data. Or at least that's part of what you're saying. And data as code, it doesn't really make sense. Because, who wants terabytes of I don't even know what that would look like, honestly. I mean, code is data in the first place, in a sense, as far as the machine is concerned. Am I understanding the problem correctly? This the traceability and the revertibility and you know all that stuff, all these problems are unsolved for data, broadly speaking.
They're each solved in a piecemeal fashion. So if you wanted to build this entire story right now of like, hey, can I detect those changes? Can I use statistical validation to determine what the impact of those changes might be? Can I filter effectively without having to manually go in and delete rows in a database? That's terrible. I can't even imagine how that would be at genomic scale when you're like, hey, I've got 18 petabytes of data that came in. Let's go through that manually. Like, no, not going to happen. So there's tools that you can automatically, you know, these concepts, they're not new. The theory of them, statistics goes back many hundreds of years. So you just implement that, and a lot of people have already implemented these techniques in packages. The trick is those detection algorithms and their implementations, they're not typically built into a data engineering ingest layer. So you don't buy a database from somebody and it comes with data validation checks. You need a third party to bolt onto that says, okay, now everything that's coming in here has to meet these rules. And also on the output side, when you're going into the model, you might be joining a bunch of tables together and getting a data set that you're going to use to feed into whatever implementation you're using. You can go and shop for that and get a package that'll do that validation, or you can roll your own if you're a masochist. That'll do effective, full screening of all that data. And then on the output of the model, you can do the same thing again. And you need monitoring and as Jillian said, lineage. And that whole end-to-end concept is data lineage, to say what changed, and then bolting on the validation checks to each phase of that. Nobody has that full end-to-end built out yet. Some companies are really far along on that path and will be done in the next 2 years to have that full story done, but it's still too nascent.
I would also say there's a big issue with the size and resolution of the data just constantly increasing faster than the scientists or the people who are deploying infrastructure and pipelines and things like that in the background can really compete with. So for example, I'm working with a company now that within let's say 4 months, I think it's about 4 months, 10x the size of their data. And it's well, we can still do all the same things, right? And it's well, we can, but it's it's 10x the data size. So on a good day, it's going to take 10 times longer. But often these things don't scale, right? There's a lot to be said for okay, how do you deal with an array that's billions of data points long? Can you read that in a memory? How much of a machine do you need to read that in a memory? Are the statistical kind of tools and tool sets that we're using, are those even applicable to that much data? Like back in the day, if you're doing statistical methods, you would apply something called a Bonferroni correction, which is basically, I'm running so many tests that I need to make sure that I haven't just found something just by virtue of running so many tests. How do you do that when you have, like billions of data points and you have a matrix, right, of billions of data points? You have billions one way and billions the other way and everything in between. So it's it's all a complicated issue. And the scientists are cool, but could you all stop increasing your data for just a week or two? that would be very nice.
That was something that I had a conversation with one of our genomics people at Databricks many years ago. And I asked him, I was like, what's the biggest problem that you see in industry? And he said the exact same thing that you just said. He's like, it's good for us as a company, but it's bad for all of our customers who have to do the analysis, because you can now sequence the human genome, full sequencing, in millionths of the amount of time that it used to take. And he's like, these machines can just power through samples, and every year you're doubling the size of the data, or it's an order of magnitude bigger. I can't remember what he said. If you're listening, Will Brandler, always great talks. But he was talking about just how this proliferation of DNA and all of the data is actually making it so that people can't get their analysis done in the amount of time that they have allocated without blowing their budget way up. He's like, yeah, no CTO is going to be like, oh, you have 100x the data, here's 100x the budget. It's more like, go figure out how to do this more efficiently. So it's a real challenge.
Yeah, and then we solve one problem. So I would say like specifically DNA sequencing, that's a fairly solved problem, right? Most bioinformaticians can be like, yeah, sure, I can run an NGS pipeline and it's all going to be fine. Then they start developing new ways of looking at the data and new ways of tagging sequences. And let's look at individual cells because, why not? And like all this kind of stuff. So as soon as you figure out one problem or like one, type of data or one data structure. So let's say like genomics data is one like specific type of data. Well, then there's single cell, and then there's like images that come from a microscope. And then there's let's figure out how these proteins are actually like positioned in a 3-dimensional space. And, it goes on and on and on, and it moves. I think the data, in my opinion, the size, the complexity, and like the sheer like variety of the data moves so much faster than the software and the computational capabilities.
Mm-hmm.
And Jillian, how are you seeing people handle this increase in scale?
Like crying? I don't know. I mean,
like just spending more money on compute, or do they change their techniques, or how do they handle it, or other than crying?
So it's a little bit of both. That's kind of like, been like my whole career strategy, and how I make my money is like I find the people with the interesting problems who are like right on the cusp of that. Like we have a data set and we need to increase, and either we already have increased it or we're about to increase it by 10x. Like, what can we do? I do a lot of like parallel computing. I work with, so specifically I work with data scientists, which has always been really interesting to me because it's more of like a people problem than a computational problem, which I personally find more interesting. And quite oftentimes, and sort of in like the spirit of DevOps, I always see it's a collaboration. It's not like I'm working for them or they're working for me, or, like vice versa. We're working together on kind of, an equal scale to get this research out the door. But quite often, because they're data scientists, their expertise is in the science, and like biologists are wild, right? They understand more about like some subfamily of, proteins that nobody's even heard of before than like I know about my own children. All right, like they are all in on their research. They're always very cool people to talk to. And so so with that said, they're not computer scientists for the most part in bioinformatics. They don't have any kind of classical training. They're like, I'm gonna hack together some stuff with some Python, or like Perl. It was all Perl back in the day, and BioPerl, because Perl saved the human genome. People, for anybody who wants to make fun of me about my Perl days, so a lot of times there's a lot that can be done to just go through their code and apply kind of methods that are going to work. So one thing that I do a lot is I do a first pass and I just see like what can be vectorized. What can we vectorize out of this? So specifically in the Python or like the R tidyverse, there's this package called NumPy, which is, a way of creating like arrays and matrices. And they have a lot of like very optimized like ways of computing on arrays. So like a lot of kind of like linear algebra stuff for those of you that are fondly remembering your math days. So that's always like the first pass. And then the second pass is to see kind of what sort of data they have and can we give it some structure. And that's just kind of all over the place. It really kind of depends on what it is. Usually it's something it can fit into either some kind of matrix. So like, for example, imaging data is a matrix. You have a matrix where each point in the matrix corresponds to a pixel in your image, right? And then other types of data are, you can throw those into, something like a data frame. And I think that's becoming like the most popular method that I'm seeing so far. It seems like, like these Parquet files are getting really big. And so, for example, like AWS Athena is really kind of pushing this sort of idea of like, okay, transfer all of your data into Parquet format, throw it on AWS Athena, and then let us just like scale out all the, everything for you.
Got it. That's interesting. And just for anyone who is not aware of the definition, do you mind defining vectorization?
I think I do. I'm not sure what the definition of vectorization is. I mean, it's like it's black magic underneath the hood. So you could have a for loop and you could say like, okay, so let's say I have an array and I want to add one to it. One way of doing that would be to have a for loop and say like for element in array, element is equal to element plus one, right? And that would be one way of doing it. Or you could pass it to a vectorization library and you could do that. And sort of the notation would be like numpy array plus one, and then it's smart enough to know underneath the hood to apply that to each element in the array. But I know at some point I learned like what is actually happening behind the scenes, and now I really don't remember. It's been a while, you guys. Had kids, my memory.
I was always good at math, but matrix math and vector math always confused me. So. When I hear that, it sounds like Star Trek to me, you know, realign the phase inducers and blah, blah, blah. And okay, cool. I'm glad that's working for you guys.
Yeah, it's the underlying tech of a lot of machine learning libraries, even the ones that people don't really talk about these days that much. One of my favorite libraries that's out there, and this makes me a super nerd, for at least for Python libraries, is stats models. I don't know why. I just love it. It's not that the APIs are exceptionally designed or anything. They are very good. But when you dig into the source code, you start seeing that everything is referring to compiled libraries. Which there's another library that's just like that. It's the one you just mentioned, NumPy. NumPy is this shiny Python veneer over a absolute metric crap ton of C code that has been optimized and compiled against your runtime, your operating system that you're installing it on. And those vector optimizations that happen, whether it's going to be truncating that to a sparse matrix where you're saying, hey, I've got a crap load of zeros in here, I don't need to store those. I'm just going to default to say if this data is missing at this vector position, I don't need to hold that into memory. So it becomes much smaller. If you're like, hey, I have 99% sparsity, I'm going to store 1% of the data in this vector representation that links to a hash map in memory. That register, I can say, do this operation, this multiplication, division. If you store a bunch of vectors together, it's a matrix. I can do stuff like invert that matrix and then take the dot product of it. And those operations are really efficient. And from a thread execution point, it's all done in parallel. So that's why you get this like blinding fast performance. And it's interesting to hear you say, Jillian, that the first thing that you look for is stuff like, what are the optimizations that I can do with respect to data structure storage and within that code? Because everybody that I've ever met in industry or ever talked to that is really good at getting things out the door and being able to do an effective code review in the ML space, data structures are the first thing that they look at. They're like, hey, how are you storing this in memory? Yeah, it's cool that you have this fancy algorithm, whatever, and I'm sure it works great, but how is that algorithm actually doing that math within the computer? And if you're storing it as a list of Python lists and then trying to multiply another list against that, that's why it takes 40 minutes to run. Let's convert these into vectors, and now it executes in 17 seconds. So it's good to meet another random person who sees that exactly the same way as other like seasoned professionals that I've worked with at Databricks. That's cool.
That's good then. I like to know that I'm in good company.
Yeah, that's interesting. Typically when I look to optimize a workflow, vectorization is very important. And if you've ever looked to figure out what is the best way to loop over a pandas data frame or a NumPy array, those Stack Overflow posts that just have a chart of essentially 7 different methods, and on the x-axis is scale, y-axis is time. Those are awesome, so go check them out. But yeah, then data structures is a great approach. But also, one thing that I think people often miss is removing essentially processes that aren't essential to the end goal. Oftentimes, people bring stuff from point A to point B that isn't needed. So trying to minimize down things in production is often really, really helpful. And Jonathan, I know you've been quiet for a bunch of this. Do you have any thoughts on how to improve runtimes, maybe in the DevOps space, or whether it be data engineering or anything?
PHP.
Not really. I mean, the PHP, yeah. Stop using PHP is a good way to increase the runtime.
Try JavaScript.
So, I mean, that's not an area where I have a lot of expertise. I mean, I have worked on doing profiling, so I maybe that's my general advice. The first thing to do is profile what's wrong. Don't just make blind guesses about. I think this looks. Sometimes you can get right. A well enough trained eye can see patterns in the code that are going to just be bad. But once you're past that surface level, you do some profiling before you try to optimize stuff. See where the bottleneck actually is happening, and that's something that so many people forget to do. And they're like, "Oh, I have a memory leak, or my CPU's, going, 100% or whatever," and they just start doing things, and maybe you're lucky and you get it right, and it's better now. Actually, very recently on Stack Overflow, in fact, I saw a post. Somebody had something they were doing in Go was eating 100% CPU, and they asked, "How do I optimize this?" And the answer was one of those "let's just try something" things that actually ended up breaking the entire code, but it got accepted because it stopped eating CPU.
CPU
Somehow,
went to zero.
Yeah, CPU literally went to zero. Basically, it was a tight for loop waiting for an event to happen, and the solution was just return early, effectively. It wasn't quite that simple, but that's effectively what happened. It was just do an early return if you don't get an answer, rather than actually waiting for the loop to complete properly. So, yeah, benchmark. Find out what the actual problem is first before you try anything. That would be my general advice that I think probably applies to even data modeling and ML.
I could not agree more that I see that more in the people with just enough CS knowledge who are getting into data science these days that want to focus on, it's really cool that we're solving this problem with ML, but they have enough computer science understanding, but not enough experience, where they want to go through, as the old saying goes, it's the root of all evil when you're writing code. It's that whole premature optimization, where you're like, hey, this is going to run slow, even though it's just a hunch, or I think this is going to be bad. And then you introduce all of this crazy complexity and spend all this time making something that took 15 nanoseconds in execution to run in 4 nanoseconds. Meanwhile, your code, when you have to now move on from your prototype to creating your first, release version, it takes you 6 months to write that code because it's so insanely complex, because you optimized it ahead of time. And then when you need to change it a year from now, everybody's like, we need to rewrite this because nobody knows how this works.
I was helping a startup last year. When I was introduced to them, they had some terrible database performance. This wasn't ML, but it was a simple database, but it was performing terribly. And their customers were experiencing timeouts and other errors as a result of timeouts. And their solution, which honestly wasn't a terrible solution in the long term, but for this problem it was overkill. The solution was to switch databases and re-implement their entire data layer. No, they needed to do that, but for other reasons.
Okay.
And so I joined, and I'm like, maybe we could do some data profile, some performance profiling, and see where the slow queries are. Within 2 days, we had it working effectively for customers, and they spent weeks on this problem. Mm-hmm. And so
to Mongo.
Effectively, we post. Yeah, it was almost that simple. We ended up postponing that rewrite, the data layer rewrite, for months because it was it still needed to happen, but it became something that was no longer urgent, and it just took a couple days of. The main reason it took 2 days to do the profiling was because they weren't doing very good DevOps. Their release cycle was slow and everything, but.
Yeah, I want to piggyback on that and say context is so important. This is something I kind of struggle with sometimes, when I'm talking to the software people, because I feel like they get a little bit hung up on I need to have these elegant abstractions of this thing. And it's do you though? Do you really? So for example, like last year or something, I was working on a project and there was this one step in this pipeline that was like really, really not optimized. And it took like a couple of hours to run. But the thing was, they only needed to run that step like 2 or 3 times a year because it was linked to a physical process that could like only happen a few times a year where they had to like add new test kits, and it was like this whole process. So it's like, well, it's the least efficient part of the code, but do we care? And the answer was like, no, not really. It happens, a couple times a year. So I mean, if you wanted to like say how many nanoseconds a day it's running for, you probably could. And so having that kind of understanding of like sort of where the priorities and what's happening where is also very, very important.
Yeah, 100%. I couldn't even begin to communicate how many teams that I've worked with while I was in the field at Databricks, where you talk to this seasoned sort of salty data engineer or a software back-end software engineer, and they're like, well, we need to create these layers, as you said, Jillian, these layers of abstraction. We need to have a builder interface where, hey, we need to do a factory pattern here. And my response at first was like, do we really need, like, I'd go home and like crack open a couple of software development books and be like, yeah, I know the Gang of Four said this was super important. We're not really using an OOP language here, and it doesn't matter if we're following a pattern anyway. This is not law. This was generally accepted at the time that book was written as being way better than what came before, which was script garbage and just spaghetti code everywhere. So setting constraints on a language that was available at the time, it was predominantly around C, and then later people applied it to Java, which is an OOP language. But modern languages, these high-level 5th-gen languages, as the things that we've talked about on this podcast so far, let me see if I can enumerate them. Go, 5th-generation high-level language.
Mm-hmm.
R, maybe a 6th generation or 6th level, incredibly powerful statistical language. Python, 5th generation, extremely high abstraction language. All of these interpreted languages, you can do functional programming, you can do OOP, you can do declarative, you can write the crappiest script that you could ever imagine in these things. They will run, and the computer's pretty good at rewriting your code for you. The interpreter is. Design patterns and execution, if we're not talking about a compiled language where we have to handle memory management, most of the languages that people are touching these days, we're no longer worried about design patterns as much, unless you get to a level of complexity of your project that is so extreme that you need levels of abstraction, or like, hey, let's eliminate 80% of this boilerplate by creating a factory pattern here. That's what that's for. But when we talk about the importances in modern software development in ML and back-end software engineering, the way I see it is readability is better than composability. Composability is better than inheritance, and inheritance is better than chaos. And those 4 levels, that's kind of how I see code now. And the only time we need to move away from pure readability is where, okay, we need some structure here because the code is just too big.
I agree. I like readable code.
I think readability, so first off, just preface this, readability is subjective, and it depends on who's reading. It's not a static trait of the code. But I agree that readability is almost the highest concern. For most code, it is almost the highest concern, maybe the highest concern. For rare code, performance trumps readability, something in a tight loop maybe. But in general, and this is something I pound the hammer all the time when I'm coaching people or mentoring developers, readable code is the most important thing. As Martin Fowler says, any old fool, or paraphrasing, any old fool can write code that a computer can understand. It takes a good programmer to write code that another human can understand.
I like that.
Yeah.
I'm going to steal that. That's like right up there with the, documentation is most important for me in 5 minutes when I've forgotten what this does.
You know what the litmus test that I use now, which actually sort of makes me chuckle a little bit in the back of my head, is when I've read an implementation, if I can strip all the comments out of it, which the only time you should be writing inline comments in code, in my opinion, is when you're reminding your future self that this was decided for a particular reason because of things outside of the code base. Like, hey, don't forget, we're doing this because there's a tech debt over here that hasn't been fixed yet. When we fix that, remove this crap. But if I remove all of the comments and even the doc strings from methods and functions, and then I can send it to somebody, like one of my fellow employees in the field at Databricks, who has no context on what I'm working on, and if they're not impressed by the implementation, if they're like, yeah, cool, I guess, it seems pretty simple, then I'm like, I nailed it. Yeah. That's how I know if it's not impressive to somebody who is enthusiastic about software development. But if I send it to somebody and they're like, whoa, this is super awesome, I'm going to need a couple hours to figure out what's going on here, I know I have to refactor the code because it's just too complicated.
Yeah, I agree with your sentiment on comments too. Comments should only exist when they're necessary to explain why. They should never explain what or how. That should be obvious from reading the code. The rare exceptions are when performance is of utmost criticality. If you have to do something with a reverse for loop for some reason because of memory optimizations for your CPU architecture or whatever, maybe you want to explain that. But those are so rare that they're the exception that prove the rule.
And they should be buried, in my opinion.
Definitely buried.
That should be
behind a well-named function.
Yeah,
highly performant for loop implementation is the name of that function.
Yep.
I had that happen to me this week. I was timing two different what I thought, what looked from the documentation like two different like syntaxes for accomplishing the same thing. It was not. One was like significantly faster than the other one on my billions of data sets that I was profiling on. So I actually put it in the comments so that I wouldn't like forget about it and revert it back to the previous one, because I'd already done that like 3 times, and then I was like, why is this so much slower? I don't understand. And then I was like, well, let me just try this, and then I realized, oh, okay. So there's a comment that says, I don't know why, but this is way faster than the other syntax that's supposed to be exactly the same. Pandas, I'm looking at you.
There's some nefarious things that happen with pandas, by the way, where you write basically a lambda to apply some sort of function to everything row-wise.
Yeah, but once you've applied, like that's the devil. Like you're in no man's land there.
Yeah. But you can write that and do a unit test on that. Where you're like, hey, I'm going to mock up, 1,000 rows of data with all of this, different distribution of data, and you run it. And you're like, yeah, that's pretty fast. Like the whole unit test executes in, 0.3 seconds. And then you run it on an integration test, and you're like, whoa, this sucks. Like I'm calling this function that I wrote, and why is this taking 38 minutes to run on, 1.5 trillion rows of data? And then you rewrite it against that test data set that you've generated, 1.5 trillion rows. And you're like, hey, I got the runtime down to like 2 minutes. This is awesome. And then you run that against your unit test, and it inverts. Uh-huh. So it's like an algorithm on small amount of data appears to be terrible, and then but it works better at extreme scale. And Pandas is full of stuff like that. A lot of times, as you said earlier in the podcast, Jillian, take that Pandas data frame, it's all just NumPy. So extract out the NumPy elements and then use NumPy operations. You're like, hang on, now it's way faster. Is something wrong with Pandas? It's like, well, sometimes it's not intended to be used the way that people use it. But if you are down for some linear algebra in base notation with NumPy, that's going to be fast.
Yeah, but pandas are like using a data frame. I use it as like a cheap way to organize data. And because if it's in a data frame, you're supposed to get anyways, the vectorization like off the, just like built in, right? Like if you're doing something against a column of data, it's supposed to be vectorized until you get into your fancy functions with apply, in which case it's anybody's guess what happens then. We don't know. It's all black magic then.
Yep. Yeah, I remember a couple years ago I implemented a simulation framework for switchback tests. And the simulation framework was essentially a bunch of Monte Carlo simulations looped with a permutation test. So it's just like millions and millions, maybe even billions of for loops. And what I initially built was a pandas implementation, and that was slow. Like it really did not run. And then I moved it over to NumPy, and it helped a bit. But there are also some sort of out-of-the-box solutions, like Modin. If you just change import modin.pandas, or whatever the import statement is, instead of raw pandas, that I think had a 3x improvement without changing any code. So that's a really high ROI solution. And then I'm a huge fan of Numba, which actually compiles for loops down to machine level code, and those run like lightning as well. But yeah, you can sort of convert the code itself, but you can also try to parallelize each of the streams of, let's say, a Monte Carlo simulation. So there's lots of different angles you can take, but big fan of Modin as like just a one-line change, and it usually leads to improvements.
Yeah, I've been getting really into Modin recently. It seems like it's really like matured in the last like 6 months to a year. So I was benchmarking a bunch of code against that. And one of the things that they do say is like, oh yeah, it should speed up your apply, and you can go. It has like a very readable dashboard. I really like the Modin, or I guess it's actually the Ray dashboard. So you use Modin and you set Ray as the execution backend. And then, it says, go look at the dashboard here, and you can actually see that it is executing everything in parallel. And you can run, you can run something fancy. I just run like htop on the node that I'm on, and I just take a look at like how, is this actually multi-threaded? And yes, it is. I guess the biggest problems that I've had with that, though, and maybe you guys have some advice for me now that we're moving on to the me and my problem segment of the show, is that at some point, like when you have these really large data sets and you want to run parallel operations, your task graph gets so large that like managing the task graph ends up being the thing that takes the most time, as opposed to actually doing the computations, because I keep running into that wall lately. How do you guys deal with that? Can Databricks deal with that? Like, should I just buy Databricks and that's the solution?
It most certainly can, in a number of different ways. So it's funny that you mentioned Ray. The team that I'm on just did the integration of Ray on Spark, and we got to play around with that library. It's awesome. And the team that built it and maintain it are also awesome human beings. Just fascinating to work with. And then, but for the question that you asked, the way I would first approach it is, if it is inherently parallelizable, and you don't have any cross dependencies across rows, you can kind of get away with it really simple. Just create a synthetic grouping key on your data. It's just an arbitrary, like, generate a window function and just assign a group membership to a throwaway column. Group by that, and then use vectorized serialization, deserialization with pi arrow, and you throw it into a pandas UDF. So on every Spark executor, you're going to have a certain subset of your data set that's going to be in pandas. And then once it's in the executor, the worker on Spark, you can do whatever you want. You can say, hey, I'm going to strip that out, throw it into NumPy. I'm going to use Numba if I want. And you can, if you need it to scale, and this is what a lot of our like genomics and health and life sciences customers do when they're like, hey, we got a couple of petabytes of data we need to process, and we're doing this on this beefy machine that we have on-prem, and it takes 36 hours to run this. After a couple of days of us hammering away at a prototype, like, hey, as long as budget's not a concern for you and you don't mind spinning up 500 VMs in the cloud, and they're like, whatever, we don't care.
We have VC money, it's not ours.
Yeah, we spin up a lot of instances, and we're like, all right, we have 12,000 CPU cores available to us on this cluster. That job now finishes in 8 minutes. So that's what you can do with Databricks. It's pretty crazy.
Do you guys have, so one thing that I've been getting asked about a lot, and I'm still kind of reasoning about how I can talk about this in a way that's understandable to the techie people and to the scientists, because I have to live in both worlds. But it's this idea of like adaptive scaling. So let's say with the example that I used earlier, where in 4 months we moved from a data set that was 200 million data points, although it's in like a matrix, so multiply that to 2 billion. So that 10x the resolution of that data. And I mean, the most clever way to deal with that is to be like, I'm going to have my modin data frame that has my points, and then I'm going to have a array cluster in the back end, and then I want to set my array cluster to be adaptively scalable, where like at minimum it uses, 10 nodes on like an ECS or a Databricks cluster, I guess. And then, but if it needs to, it can scale up to 100 because, what the hell? It's not my money, it's the VC money. So why not? But like I see people like more and more interested in this kind of solution as time goes by. I'm not quite sure like why. I've been trying to figure out like why it's entered sort of the public consciousness of the people that I'm working with, and I feel like there's always like one source of truth that I can go and and like find and then heavily question them. So I'm going to do that. But is that kind of computation possible, and is that something that you also see an increased interest in?
One meta point is that I think TCO, or total cost of operations, is more at the forefront of a lot of businesses, and they just want their compute to be as cheap as possible while meeting a given requirement. So that is a potential explanation for why. And then at Databricks, there's a bunch of auto scaling concepts, whether it be in compute or in sort of a SQL endpoint. And essentially what happens on the back end is we have a gateway that queues into different compute resources. And if that gateway has a very large queue, it then scales up the compute resources. And so that's sort of one way to handle this, is you have sort of a meta driver almost that will determine the load on each of the compute resources. And if the queue is too large or too small, it'll scale up or scale down accordingly. And then one other consideration is that typically workloads aren't even, so it's helpful to have sort of a fast track or a slow track for small or big operations. But yeah, just sort of managing metadata about the queue or about how much backup there is in the system. That's a relatively simple way to go about it.
Yeah, and we try to tackle all of that stuff as just opaque. If you're an end user who's trying to rationalize about how do I auto scale this for cost, or for just, if you don't care about your budget, you're just like, how do I get more compute resources and not have to constantly be adjusting? If you're going in and starting up a cluster or something every day, and you're like, well, it was 14 nodes yesterday, and it was kind of slow. Do I need 18 nodes? Well, how do I configure those 18 nodes? Do I need to change my code? So that's what our platform, that's one of the many, many things that our platform does for users, is you don't need to worry about any of that stuff. We have written algorithms that figure all that stuff out for you and autonomously handle provisioning of machines in whatever cloud environment you're in.
Those are my favorite libraries that like abstract. I was kind of harping on abstraction earlier, and now I'm right back on it. But is abstracting like the execution layer away from me? Because I'm like, there's a computer there somewhere. There's some storage, probably on a similar network. I don't know. And I don't really want to have to know. I just want for my stuff to run. And I always kind of feel like, too, when I'm talking to scientists, if they are worrying about those sort of details, I'm kind of like, I haven't done my job here. Like, you shouldn't need to be worrying about that. We need to like get back to basics and figure out what's gone sideways somewhere. Is Databricks like just a big HPC cluster? Am I allowed to ask that?
It is not. We don't support HPC.
Why not?
I don't think there's a big enough market for it, because I think most people who are using HPC are doing it on-prem, not just because they want extreme performance. It's usually because they're dealing with something that they really don't want to get out onto the internet. The data is so insanely sensitive, and they have so many security protocols around the ingress and certainly the egress of the data from there. And it's also really challenging to get that amount of hardware in the cloud dedicated in such a way that could compete with an on-prem HPC system. You're like, hey, the way that those racks share memory, the way that they share GPU resources and CPU resources, where you're like, hey, I can put 50,000 CPUs all in the same machine. It's not physically doing that. Server blades aren't built like that. It's just network architecture where you're talking about your constraint is the laws of physics. Like, what material needs to be, do the bus bars need to be made out of in order to connect this server tower to this server tower? What is the interconnect there? Is it bare metal? Is it some sort of unique alloy that we're using? Is it just massive pipes of fiber optics? There's a lot of considerations that you have control over when you're building an HPC system on-prem. In the cloud, it's like, it's probably in the same data center, but they're all virtual, and you're not going to get the performance out of it. I'm sure that every cloud is offering those. I'm pretty sure Amazon offers something for HPC, and Azure does as well. But that's like an ephemeral thing. It's not going to be an apples to apples comparison to what you'd get in your own data center.
That was a good answer. I was mostly asking for like inflammatory reasons, because a lot of times the response to that is like, HPC is going to die, and then I could be like, no, it's not.
Oh,
and and
no,
then we can rip off that for a little while. But that was good.
I don't actually see a killer to HPC, because it does things that no other system can really effectively do. Like, there's a reason why people build those systems, and they excel at what they do. So I wouldn't listen to people who are just trying to.
Nah, I'm not going to. I think. Well, sometimes that person trying to instigate is me, but I'm planning on riding the HPC wave for the rest of my career before I go to Acadia and pitch a tent someplace with no internet. It's the retirement plan.
So, do you think that quantum computing will be adapted to potentially augment HPC in the next 10 to 15 years?
I don't understand quantum computing. I don't know if it's like, maybe I'm just like not quite smart enough to understand it, or if I haven't seen the right sort of like diagram that makes it fit into my head, or what it is. But like, I don't get it. I feel like it's one of these things that's thrown around. It's a little bit like AI to me, where it's like, there's stuff happening behind the scenes. I don't know what it is. So yeah, I don't really have an opinion on that either way. I don't really understand the topic well enough. What do you think?
I mean, I think it lends itself to some of the activities that we would take on from applied traditional statistical methodologies, where you need to just brute force your way through a potential solution, and the qubit states can do that exceptionally well and much faster than silicon-based architecture. I personally think it's a little bit far off for getting commercial versions of these. And then, a lot of people are talking about the hardware and the tech, and they're like, yeah, it's going to come. It's going to crack all the passwords. I'm like, no, it's not. They'll adapt. But the focus that people have been having is on the hardware, and of course the bespoke implementations of how you can apply that hardware to certain problems. But nobody's really focusing on, hey, what does the compiler look like? What do the IDE plugins look like? What does the dev process look like for creating this stuff? How do I write tests? What is the test framework for this? How am I going to, write an algorithm in some language that this thing understands? Because it's not running Python. It's not running Go. It's going to have its own, assembly language instruction set that's going to go and talk to that hardware. So I'm sort of waiting for that sort of stuff, and then be able to make a decision. Like, okay, I could see the utility of this. For right now, it's cool. It's a novel concept, I think.
I'll just throw in my 2 cents on that, even though I don't really understand HPC very well. But I have a sense that quantum computing, and I think even analog computing, are kind of, they're going to, I don't think they're going to fundamentally change the way a computing works. They're just going to fracture it. And I say that in the same way that like we now have CPUs versus GPUs, doing different types of work. I think we're going to start to discover that quantum is great for certain types of work, and analog computing is great for certain types of work. And it's just going to make things more complicated in the sense that, like, it's no longer just throw it on AWS. It's like, make sure you get it on the right AWS cluster that has those analog compute resources or those quantum compute resources or whatever. It's just we're going to have more moving parts, I think is going to, at a high level, that's what it's going to look like.
Totally. I mean, that's how that, like, as you said, that fracture between GPU and CPU, there's tons of use cases that are out there that, like, could you execute it on a GPU? Sure.
Yeah.
How is it going to run? It's going to run like crap.
Right.
Because GPUs are not designed to do this thing.
Yeah.
Just the same way that you're doing, the training of a deep learning model where you're adjusting weights in this massive matrix of connected points in this huge graph. GPUs do that orders of magnitude faster because they're really good at doing exceptionally parallel math computation. They're really good at algebra, like really good. And when you look at the architecture of a GPU, you're like, whoa, how many parallel pipes are in this thing? How many concurrent calculations can it do at once? That's what it's designed to do. They're designed to do basically 3D modeling of video games on somebody's monitor. But that's what that is. Like, process these 347,000 objects in synthetic three-dimensional space. What do they need to do at 110 frames per second?
Mm-hmm.
It's got to be really good at just processing that map of like where to actually draw this stuff.
Yep.
But CPUs suck at that. Like, run a modern video game on a CPU, it just won't run.
Well, we're coming up on an hour. Anything we want to touch on before we close out?
Is AI going to take our jobs? Are we all going to do?
Yeah.
Or our resounding answer to that?
My hot take, no, it's going to augment our jobs like every other technology that has come along since we discovered how to farm as a species.
I also vote no. This is like the fourth round of like AI is going to, take over your jobs, specifically in healthcare and genomics. There's been a lot of several AI tools developed over the years, and each one was, there was a big kind of, everybody was worried about it, and every time it was like, it's fine, I still have a job. Now everybody knows about the ChatGPT, and so now like everybody's asking that, but same stuff to me. It's another tool that I've been told will take my job. They haven't yet. HPC for life, so I'll be fine.
For fun, I'll disagree. I think it will take our job, just not yet. Self-driving cars will replace truck drivers, and so eventually AI will be advanced enough to do some of this work, but we will then just need to pivot into different roles and leverage that technology. So if you're agile, you'll be fine. If you're not agile, tough luck.
Yeah, that's close to what I was going to say. I think it'll take some of the jobs, the same way the automobiles replaced horse breeders. Mm-hmm. But from an industry standpoint, it's not going to take our jobs. Somebody has to program the AI.
Yeah, it's going to take our job titles, but it's not going to put us on the breadline.
And as I said before we recorded, my whole job is automating my job away. That's the definition of software development. So it's not something to be afraid of. It's actually what I do.
Yeah, it's true. Code myself out of jobs all the time. It's like it's the nature of the beast. Yeah, I like that way of putting it, actually. So I do think it will get rid of some jobs, but I think like the net will remain the same. There will still, if there was X number of jobs before, there will still be X number of jobs. It's just the distribution of job titles, I think, will shuffle around a little bit.
If there's something that could like in a fell swoop kill a whole bunch of software development jobs, it would be companies learning how to embrace the proper software development practices.
The entire consultant industry gone overnight. Yeah.
It would be every time, somebody's like, we have to write this whole tech stack. If every manager on the planet just knew to be like, no, don't do that.
Buy versus build. Yep.
All right. Well, this has been a great conversation. It's been fun meeting you guys, Ben and Michael.
Likewise.
Thanks for doing the crossover episode. It's been fun.
Yeah, this has been great. Thanks for coming.
Yeah, thanks.
We voted before recording to not do picks today, but I'm going to pick the Adventures of Machine Learning podcast. For those of you who haven't listened to it yet, check it out. It should be very educational.
And for our audience, definitely check out the Adventures in DevOps podcast to get some perspective on how to think about your projects from a production deployment and development perspective. I think you'll enjoy it and you'll get something out of it.
Thanks, guys. Until next time.